In this video, we will learn about the cross product. So recall earlier we learned about the dot product. That's one that takes two vectors u and v in Rn for any n and gives back a number. By contrast, the cross product, which is different, takes two vectors u and v in R3 and gives back a vector in R3, denoted u cross v. So this is a vector, whereas the dot product was a number. So vectors in R3 are just triples of numbers, like 4, -1, 3. That's a vector in R3, as an arrow. It starts at the origin and ends at this point. And we can write this vector as a linear combination of the standard basis vectors e1, e2, and e3. e1, remember, is 1, 0, 0, and likewise for e2 and e3. Now, it's convenient or common to write I, j, and k instead of e1, e2, and e3 when you're in R3. And so for e1 is the same as for I, and similarly for e2 and e3 replaced by j and k. Now we can finally get to the definition of the cross product. So given two vectors u and v in R3, so that means u has components u1, u2, and u3. Let the components of v be v1, v2, and v3. And then the cross product of u and v, by definition, is the determinant of this matrix with I, j, and k in the top row or first row, followed by u1, u2, u3, v1, v2, and v3. And then expanding this determinant across the first row, that means it's I times the determinant of this matrix here, which is u2 times v3 minus v2 times u3. So that's what I've written here. So that's this thing here is the first component, or the coefficient on the I of our vector u cross v that we're defining. Similarly, the coefficient on j, well, we need to have a negative sign there, and then we cancel out the first row and the column including j, and then it's u1 times v3 minus v1 times u3. We take the determinant of the 2 by 2 matrix that's left over when we cancel out the first row and the second column, and that's what I've written here. And then finally, we add to that k times the determinant of this matrix here that's left over when we cross out the first row and the column containing k. So u1 times v2 minus v1 times u3. So this is the definition of the cross product. And on the next slide, we're going to do an example. Okay, so let's suppose our two vectors are u and v are given by 5, 2, 1 and 0, 3, 2. Then the cross product, it's going to be a vector. And by definition, it's the determinant of this 3 by 3 matrix. And I, j, k again is the first row. And then we put our first vector u and then our second vector v. And then we take the determinant of this matrix using expansion by minors along the first row. So we've got I times the determinant of this 2 by 2 matrix, 2, 1, 3, 2. And so the determinant of a 2 by 2 matrix is you take the product of the diagonal terms. So that's how we got 2 times 2. Subtract off the off-diagonal terms, subtracting off 3 and 1. Okay, and then we go to this spot j. There's a minus sign because remember the formula for determinant was -1 to the row plus the column. So this j is in row 1 plus and column 2. So that's where this 1 plus 2 in the exponent comes in. That's a 3, and -1 to the third power is a negative. It's a little bit easier just to remember plus minus plus is how the pattern goes when you're expanding by minors along the first row. Okay, so then we delete column that involves j and the column that, the row that also involves j, and the matrix that remains is 5, 1, 0, 2. The product of the diagonal terms minus the product of the off-diagonal terms gives this, and then similarly we do that for k. Take the determinant of the matrix 5, 2, 0, 3, the main diagonal, take their product, subtract off the off-diagonal. Okay, and then doing the arithmetic, we get I times 1 minus 10 times j and plus 15 times k. It's typical to write the coefficients in front of the vector, so that's what the order has been interchanged. Okay, so yeah, then this is our vector, our cross product. Here's another equivalent way to write it. And so yeah, so this is this answer right down here is the cross product of these two vectors. Now, the order that you take the cross product in matters, because if we switch v and u, then these rows will get switched. And when you switch two rows of a matrix, the determinant of that matrix then gets multiplied by -1. And so the dot product of, the cross product of v cross u, the order switched, would be -1, +10, -15. Now, a very important fact that holds in general is that the cross product of two vectors is perpendicular, or another word for perpendicular is orthogonal, to both the two vectors u and v that you started with. So I tried to draw that in a picture here. If u and v are pointing in these two directions, then the cross product is orthogonal. Think of this as u and v being a plane, and then this u cross v, the cross product, is the normal vector to that plane. Here I've checked it out in our specific example that we did, but the general reason is that when you take the cross product and then take the dot product with this vector u, essentially what you're doing is computing a determinant whose rows are, the ijk row is replaced by u essentially, and then there's this cross product has that row u as well, and so you're taking the determinant of a matrix with two rows that are the same, and that's going to give you 0. I should have written here that two vectors are orthogonal if their dot product is 0, and so that's why, well, what I've computed here is that the dot product of these is 0, and likewise here the dot product is 0. It'll hold in general, not just for these specific values of u and v given above. There is something called Lagrange's identity, which expresses the norm of the cross product in terms of the norms of the two vectors and the size of the dot product. And you can prove this by just expanding out all the terms in coordinates. But let's just check this in our example. So u cross v squared was this. U cross v was this, and then when you take the norm squared, remember the norm is the square root of the sum of the squares of the components, and then when we're squaring that, the square root disappears, so we get 326. Similarly, computing the norm of u and v gives this thing, and then the dot product of u and v is some number, and squaring that gives this, and magically we get the same answer. Now, the reason I mention Lagrange's identity is really to prove this identity here, which says that the norm of u cross v is a product of u and v, the product of the norms of u and v times the sine of the angle between them. And this is to contrast, or kind of similar to, the dot product being equal to the product of the norms of u and v times the cosine of the angle between them. All right, so let's jump back up here to the derivation of this boxed formula. So we start with Lagrange's identity. This was Lagrange's identity. And we replace the dot product with an important formula for the dot product that we've seen in a previous video, that the dot product of u and v is a product of the norms of u and v times the cosine of the angle between them. When we square that and distribute the exponent 2, we get this. And then factoring out the product of the norms squared, we get 1 minus cosine squared here. And then 1 minus cosine squared is sine squared. That's a trig identity. And so Lagrange's identity then reduces or gets translated to this. And then when we take the square root, we get this formula here. Now, why is this formula boxed here useful? It's because of this important geometric fact, is that this magnitude or norm of the cross product equals the area of the parallelogram formed by u and v. So u and v form this parallelogram, and the area of this parallelogram is the norm of u and v. I'll explain why on the next page. So the area of a parallelogram is its base times height. And by height, I mean the perpendicular from one side to the opposite side. And so we've got one side being equal to the norm of u, and then the height, I'm just calling it h. And what is h equal to? Well, we have to use some trigonometry. So remember, theta is the angle between the two vectors u and v, and sine theta is opposite over hypotenuse. I've made a right triangle here, and the opposite side has length h. That's my definition of h. And then the hypotenuse has side the norm of v, and therefore h is equal to the norm of v times sine theta. Then I come back over here and replace h by norm of v times sine theta. And then on the previous slide, we saw that this formula by Lagrange's identity is the same as the norm of u cross v. And so that's why the area of the parallelogram spanned by u and v is equal to the norm of the cross product. So that's a geometric explanation of the magnitude of the cross product. The direction of the cross product is perpendicular to the perpendicular to the vectors u and v. Finally, if you have three vectors u, v, and w in R3, then the volume of the parallel pipette, so this is a three-dimensional type of parallelogram formed by them, is given by the determinant of the 3x3 matrix that is shown here. Namely, the vector u has components u1, u2, u3. Likewise, for the vector v and the vector w, you throw them into the 3x3 matrix, compute its determinant, and that will give you the volume of the parallel pipette. Let me draw a picture of what that parallel pipette should look like. It's something like, well, here's the base parallelogram. Suppose we've got v and w here maybe, and then maybe, oops, didn't do such a great job drawing, but something like this. These do not have to be at 90 degrees. Okay, let's do an example from Anton, page 180, number 14. It says, find the area of the triangle with vertices A located at 1, 1, vertex B located at 2, 2, and vertex C located at 3, -3. So here I roughly sketched the positions of A, B, and C, and then we've got this triangle. And so the first idea is to make these two vectors starting at A, and one that starts at A and goes to B, the other that starts at A and goes to C. And so this vector A to B is the same as the vector B minus the vector A. So remember, this notation, vector B, is secretly the vector that starts at the origin and goes or ends at the point B. Likewise, the vector A is secretly starts at the origin and ends at A. And we've seen this formula follows from the addition law for vectors. Anyway, so B minus A is vector subtraction of, so vector B is 2, 2, A is 1, 1. So we have AB is 1, 1. You can kind of see that geometrically. If we start at A and go over 1 unit and up 1 unit, then we're at the point B. So that's why vector AB is 1, 1. All right, similarly, AC is C minus A. Here's C, here's A. Doing the subtraction, we get this. Now, in R3, these vectors you just tack on an extra 0. The reason we're going to jump to R3 is the area, remember, is given by the cross product. The area technically of the parallelogram is given by the cross product. The triangle will be half that area. So the area of triangle ABC is 1/2 the area of the parallelogram spanned by AB and AC, and we've seen that that area of the parallelogram is the cross product of AB and AC, and followed by the magnitude or norm. So on the next page, I'm going to compute or take these vectors, throw them into a big matrix that computes the cross product, and then I'll have to take the norm. So AB and AC and their cross product, so we formed this big matrix. AB was 1, 1, 0, AC was 2, -4, 0. Forming their cross product, well, what I did is expand this determinant along minors along the third column. Usually I do the first row, and that's also fine, but I notice I've got 0 here, 0 here, and so it's just going to be easiest, since I can choose any row or column to expand by minors along, I just choose the third column. Okay, so then k times the determinant of this matrix here is what the cross product is going to equal. The determinant of that matrix is 1 times -4, so that's how I got this -4. Subtract off the off-diagonal elements 2 and 1, their product, okay. And so then I get -6k. So that's the cross product. It's a vector. It has only one component. The ij components are 0. So as a vector in 3 space, this cross product could also be written 0, 0, -6. Okay. Yeah, that's what I've done here as well. And then the norm of a vector is you take the components, square each of them, add their squares, take the square root, and in this case it's just 6. So the area of that triangle is 1/2 of 6, which is 3.